The screw didn't quite hit the center. Oh, frick! I'm losing steps. Here goes nothing. 3, 2, 1. Okay, welcome back to my ridiculous 3D printer series. For all those joining our adventure just now, I am trying to build a functional 3D printer for under $50 US using mostly trash and recycled materials. And the only things we've left to do before we can print the first benchy is build the heated bed from scratch and figure out the electronics. So very little to do, just a few months left. In today's episode, we are going to concentrate on building the heated bed the way I discussed last episode. If you haven't watched that video, I highly recommend you do first to get some context, since all the juicy engineering bits were covered in there, and today is really just the actual execution. That being said, let's start by taking off the build plate again so we can work on it. In the meantime, I have botched together some crude knobs out of plywood for adjusting the bed level. As soon as the printer works though, I'll print some better ones. Okay, so the next step will be gluing the aluminum foil to the underside of the glass using this contact spray adhesive by Yahoo. No affiliation, no opinion. I don't know how well this will stick in the end because, as opposed to my test pieces, which were slightly frosted, this pane of glass is totally smooth on both sides, so we'll probably end up squeegeeing out most of the glue anyway. Speaking of glue, you don't necessarily have to use spray adhesive. Any other low viscosity solvent-based glue should work too. The reason it should be solvent-based is because between two impermeable layers of material, you'll have trouble getting less volatile carriers to evaporate and thus the glue to dry. This is incidentally why you actually want to squeeze out most, but not all of the glue. Another thing I didn't really address in the last episode was that this glue doesn't need to be able to resist high temperatures. We're really just temporarily sticking down the foil so we can easily cut out our heater strip with a knife. Later, the entire thing will be covered in kapton tape, which will do the actual work of holding the aluminum in place. Whoops, that's not good. I was about to say it went on a lot better than I anticipated, and then I ripped it. Fortunately, this shouldn't be a problem since my heating element doesn't actually reach out this far, and we're gonna peel away all the unwanted stuff anyway. So now I just need to let it dry. For me, it'll be overnight, and for you, it'll be a split second. And we're back! It's now actually a week later, which means the glue should be thoroughly dry at the very least. Why did I wait a week? Well, in the meantime, I had to set up the 3D printer as a 3-axis pen plotter because the next step will be making use of it to directly plot the shape of my heating element onto the aluminum. Patreon members will have had an extra 20-minute episode of me scrambling around to figure things out, but for time's sake, we're now just going to talk about the things I learned in a condensed version. First off, setting up a CNC turns out to be pretty easy as long as you use the dedicated stepper motor drivers, CNC shield, and stock Gerbil. Even though I'm running a reduced X and Y axis resolution of 0.2 millimeters per full step, with microstepping impossible, the results I was able to achieve were pretty promising. Yeah, it does look a little bit jagged and pixelated, but this is honestly a lot better than I expected. Courtesy of having almost no backlash in the gantry, I guess. The thing that really ruined the experience with the pen plotter was the backlash and the gear reduction of those stupid 28BYJs. Don't have that here, and the lines meet up perfectly almost every single time. Overall, I'm now pretty confident this will be capable of 3D printing even before the upcoming lead screw upgrade to increase resolution. What's not so good is that my wonderful handmade pulleys on the Z-axis timing belt setup don't really work. I mean, the entire configuration was pretty finicky even back when I made the video, but now for some reason it didn't work anymore at all. The timing belt tends to skip cogs on the pulley because they just don't mesh properly, and it constantly slipped off the idler bearings, jamming the drive pulley. It was so bad I ultimately had to swap out the bearings for some real idler pulleys I bought for my laser cutter project. Now it almost works. Hopefully that'll do. Fortunately, those wooden pulleys were only ever meant to be temporary. I only need them to work long enough so that I can 3D print some proper pulleys and idlers. And a benchy, I guess. I think this should serve you as a lesson. Quite often the cool things you see people build online don't actually work off camera. Now I'm trying to build machines that do still work after I'm done shooting a video because I want to use them. Duh. Which is part of the reason why my videos take so incredibly long, but apparently I don't always succeed either. And with that shameful admission out of the way, let's cut off any overhang of the tinfoil and mount the plate back on the 3D print plotter, pen plotter, 3D print plotter, pen 3D plotter, 3D pen printer, maybe. Whatever that thing would be called. And yes, your eyes didn't deceive you. I literally screwed the X-carriage of my pen plotter onto the X-carriage of the 3D printer to get a convenient spring-loaded pen holder. Not a great design to let the tip of the tool have so much mechanical advantage over your linear rails, but in this case it seems to work pretty well regardless and was a lot easier than building something from scratch. But with the printer ready to plot, let's talk about the thing we want to use it for. As I've mentioned last episode, this is the layout for the heater I came up with. We know we have a voltage of 19.5 volts with 6.15 amps at our disposal, and I had measured the resistance of my aluminum foil for a 10mm wide strip. Knowing current and voltage, we can easily calculate the resistance our final heating element should have and see how much aluminum strip we would need. At 10mm, however, the heater strip would have been far too long to even fit on my glass, so by decreasing its width to 5mm, we effectively double the resistance, which puts us at just over 6 meters in required length, and those can easily be fitted onto the glass. Unfortunately, there doesn't seem to be a good way to do that, other than to subtract the total width of the heater surface you aim for, i.e. the sum of all those little horizontal bits, from your total length. The remainder can then be divided by the number of vertical strips you want to have to get their length. So basically, the little slack between having one too many and one less than the ideal number, which might include half a run by the way, gets taken up by how close these get to the edge of the build plate. And yeah, the likelihood of actually getting the resistance I calculated is pretty low because of the rings I have around the mounting holes and this difference here not being accounted for. Plus, I don't know what all these corners will do to it, but if it deviates too much, I can tweak the width of the trace with this parametric function and make another one. I went ahead and exported the G-code, which turned out a lot easier than I expected, thanks to a tutorial. Tell you what, compared to other programs, there really isn't much in the way of documentation for FreeCAD out there. I also calibrated the machine as best I could with a 0.2mm resolution, which clearly isn't great. So we're ready to prepare for the worst, but hope for the best when I hit the send button. Fingers crossed. 3, 2, 1, go. That's now running at its maximum feed rate of 3000 millimeters per minute. And the Z-axis is very slow as usual. Off we go! The screw didn't quite hit the center. Oh frick! I'm losing steps. No, no, stop, stop. Oh, damn it! Ugh, what was that? And of course the pen did leave some slight engravings, which would have been handy when the ink in the pen can't travel down fast enough and it stops drawing, but now it's just annoying. This is so weird. Yesterday evening I did a test run and everything was perfectly fine, but why is it losing steps now? Well, to be honest, I had the same problem yesterday evening, and I figured it was the connector on the stepper motor slipping out, so I put zip ties around it, and it still didn't work. Presumably these stupid connectors slipped out this time, because whenever the stepper motor moves, it moves this cable, and that may have moved the connectors. So I'm gonna put a frickin' weight on there. That should do. And let's try it again. There we go, attempt number 2. Maybe it'll work this time. 3, 2, 1, go. Oh, for heaven's sake. What on earth is... This is cursed. The screw is even less centered in the circle. I guess I'm gonna try decreasing the feed rate a little bit. Maybe this pen has just too much friction on the aluminum for the steppers to keep up with. Attempt number 3. If this doesn't work, I don't know what I'm gonna do. Send it. And dang it. For heaven's sake, what is it doing? That's what it should have looked like, minus the big missing chunk over there. That's what I hate about CNC. It always goes wrong every single time. It's a frickin' waste of time. The time it took me to set up the machine and fail 3 times, I could have just measured the entire thing by hand with a ruler and cut it out. And why didn't I do it? Because yes, it's more of a pain in the butt than having a machine do it. So anyway, I need to swap out the aluminum. The old one peels off quite nicely with some isopropyl alcohol, which also helps dissolve any remaining glue. Now you might be wondering, why am I using the machine to plot the shape in order to cut it out by hand, instead of just mounting a knife on it and have it do the cutting for me? Well, it's kinda risky because the aluminum tends to stick to the knife and bunch up, tearing like it happened with a pen. Plus, I don't want to deal with the more complicated software required for the moving offset of a drag knife. But I've had enough of those shenanigans now. I definitely don't feel like cutting anything out anymore, so I guess a knife is what I'm gonna try next when I finally get this working. Apparently I did quite well on my first glue up, since it's actually quite hard to get this stuff on without any wrinkles. However, this time we're gonna make the machine cut it directly, except I'm not going to use a swiveling drag knife like you'd see on a vinyl cutter. I'll actually install a fixed knife. And in order to make this work, I exported my heater shape as an SVG, used Inkscape to split it up into 2 separate files, one with only horizontal lines, the other one only vertical, which then allowed me to export 2 separate G-code files that I can run one after the other, manually switching the knife orientation in between. Now, while fiddling around setting this up, trying to get it to work, I had a whole new host of difficulties, with the Y-axis suddenly losing steps for no apparent reason at all, despite having turned the feed rate down to 2000 from the original 3000 and decreasing accelerations. But now, I finally found the culprit, and wouldn't you believe it? A single strand in the Y-axis fishing line broke, and the resulting loose wire occasionally got tangled in the windings around the drive drum, effectively blocking the entire carriage. Now, when I installed it, I did mention that this fishing line is technically too stiff and that I would expect it to eventually fail, but honestly, I did not think it would happen this early. So I guess I have to replace it with a slightly thinner nylon-coated fishing line I use on the X-axis. However, being thinner, I don't really trust this stuff to handle the inertia of the print bed at high accelerations without being too springy longitudinally, so I'm doubling it up, running 2 in parallel to make up for that. As for the knife, it needs to be extremely sharp to not make things even worse than they already are and turn your heated bed into this, so I think the best bet is to use a brand new disposable blade, as those are usually way sharper and smoother than any of us common DIYers could ever hope of sharpening something ourselves. Of course, since adding an entire inch of additional height to a gantry of, questionable rigidity to begin with, I'm actually going to use a piece of these snap-off utility knife blades instead of the X-Acto. and although the reasonable solution would be to just stick this in the X-Acto knife handle, it appears we don't have any of those slim aluminum handles around anymore, so I'll have to see how I handle things, because this fat one doesn't fit my machine. Are you ready for attempt 4? I'm not, and if this somehow gets messed up again, I'm gonna go buck wild. And off we go. Well, so far so good. At least it is cutting without tearing the aluminum. I did keep feed rate and accelerations down because I figured the faster it goes, the more likely it'll skip steps, and the Z-axis seems to work significantly better after I grease the lead screws. Shocker, huh? Well, that actually completed successfully, and probably did a better job than I could have by hand. Mind you, this was only the easy part. Now I need to rotate the knife and re-zero it on the corner of this piece of masking tape, because if you think about it, flipping the knife will create an unknown offset from the position the computer thinks it's at, so I need to manually move the gantry to the new actual zero position without the computer noticing, and how accurately I manage to do that will determine how well the cuts line up at the corners. Then the G-code is the one I have not tested yet, and I really hope it doesn't start tearing off the tinfoil doing the corners. That's about as good as it's gonna get. I also did a little test of the G-code. Now I'm fairly confident it won't drag the knife backwards across the aluminum, so only thing left to do is press send and hope for the best. It is cutting. And the corners do look pretty good, I'd say. This is actually a complete and resounding success. Look at those corners. I never thought this would be possible. Now you might have noticed this time I omitted the circles around the screws, which may be owing to the fact that doing circles by cutting straight lines is kinda hard. Those circles were mostly decorative anyway, so I can easily put them on by hand. Plus, this way I didn't risk crashing the blade into those screws, which, even so, it literally almost did. It actually touched both of those screws, but only barely, and it wasn't enough to lose steps. That means I can finally move on to the next step and start peeling off the excess aluminum. But first I need to do those circles. I'm just gonna use an appropriate sized washer as a template, screw it down and trace around it with the X-Acto. And actually, this alone was enough to make my confidence that I possibly could do a better job at cutting the aluminum than the machine fall down at least a 5-story building. I literally cannot discern whether the knife is cutting aluminum or not. It just goes through like butter. While it may have been easy to run the blade along a ruler, doing the corners would have been a minor nightmare with high chances of ruining everything with a single slip. Speaking of corners, let's be very careful lifting up the foil to grab it with tweezers. Again, even a single millimeter cut into the trace will destroy everything, because that spot will end up having higher resistance than it should have, thereby becoming hotter than the rest of the heater. And yeah, if you look closely, there is a little overcut on every right-hand inside corner. I guess my vertical alignment wasn't quite perfect and should have been 1 or 2 steps farther to the right, but I don't know how much of an impact this little cut would have, and after all, we still haven't tested the resistance this thing has, because if it's too far off, I need to scrap it anyway, and it'll never be anything more than a prototype. I might just be in for a lot of practice gluing, cutting, and peeling off tinfoil. And that's it done! It turned out wonderful! Actually, the amazing thing about the spray adhesive is it primarily sticks to the aluminum, leaving almost no residue to be cleaned up on the glass. Another thing I learned already is, for peeling off the foil, you don't actually want the sharpest knife possible, as it'll cut the aluminum rather than crumpling it up so you can lift it off the glass. A slightly dull one, like the sharpest kind of dull I can get my carving knife, seems perfect. Okay, so before I spend any more time than absolutely necessary on this unproven heater trace, let's measure the resistance. For starters, I'm going to use just the multimeter, because if the result's too far off with that, there's not even a point setting things up for a super accurate measurement down to like 5 decimal places. Remember, I'm aiming for a value of 3.17 ohms. The multimeter leads have an inherent resistance of 0.2 to 0.3 ohms, so we're actually looking to get 3.19 to 3.2 ohms for things to be correct. So let's see what it actually is. 3.4 ohms. That is actually pretty darn close. That means I can set up a real accurate measurement to measure it down to like 5 decimal places. 3.3 ohms? That is pretty good! My math seems to have actually checked out alright. Now, you might be wondering, but Benjamin, how on earth do you want to measure resistances down to 5 decimal places? Surely you don't have one of these? Well, you're totally right. I sadly don't own one of these, but fortunately there's at least 2 workarounds allowing us to measure super low resistances using a multimeter, even though multimeters are generally no good at measuring anything below 5 ohms. The method I'm going to show you now I found in a blog post, which I'll definitely link to in the description so you guys can check it out for reference. The idea is we create a stable 5-volt power supply, ideally using a linear regulator like the 7805, or by adding decoupling capacitors and whatnot to an existing power brick. Then we take a medium value resistor that can easily be measured to a reasonable degree of accuracy with our multimeter, in this case 220 ohms, and put it in series with the thing we want to measure. By measuring the voltage drop across our known resistor, we can calculate the exact current flowing through it. And because the current through our test subject must be identical due to them being in series, we can then use its voltage drop to work out the exact resistance. That way we mostly rely on the voltage measurement capabilities of our multimeter, which are vastly more accurate than all the other units. Because guess how a multimeter measures current? By measuring the voltage drop across a known resistance and calculating the current using Ohm's law. And this method is exactly what I use to measure the resistance of my aluminum foil down to this many decimal places, which in turn allowed me to calculate the even tinier resistance per centimeter the stuff has, and hopefully get my heater trace within the realm of usability. But having to tie this into a circuit for the measurements inevitably brings up another question. How do I plan on reliably connecting my aluminum heater trace to any copper wire in the first place? Someone on the last episode commented this would be quite a challenge, but I disagree, since I conveniently drilled holes through the glass, I'm going to, you guessed it, simply have the bed leveling screws double up as easy electrical connections. I just need to cautiously scrub the pads with steel wool to get a fresh surface, wipe them with IPA to get rid of any potential oils, and then the washer should make good contact. For the cable, I'm going to use this high temperature wire from an old oven. As you can tell from the color code, it was originally the earth connection to the metal casing, but screw the wrong color code if it has the appropriate ring connector I need on either end. Snipping it in half, I can put the ring connector on top of the washer and tighten everything down with a nut. Okay, got the circuit all soldered up. The resistor measures in at exactly 217.8 ohms, with the resistance of the multimeter leads already accounted for, so now I just need to fire it up and measure each voltage drop in millivolts. Well, that's a bit more than I hoped for, honestly, and I'm pretty sure the additional resistance comes from the washers not making good enough contact with the aluminum. If you think about it, it's actually extremely hard to get anything into really intimate contact with aluminum, since it just immediately grows an oxide layer on fresh surfaces. I guess there are things that could be done to improve this, but you know what? I'm gonna call it good enough. It may draw a little less power overall, the screws might get a little warmer, but I'm kind of fed up with this video at this point and I want to finish it. I'm sure the aluminum itself is 3.17 ohms or less, it's just that we cannot measure it because the connections have too much resistance.
Moments later.
Yeah, if I measure from aluminum to aluminum instead of from washer to washer, I actually get 3.1616 ohms. So it really is the connection between aluminum and washer. Although I also don't know how much resistance the steel washer has, so it's a success. 3.17 ohms, we definitely got it. I don't know why it blows my mind like that. I mean, I did do the math. I measured the resistance of the aluminum and based the length of my heater trace off of that, so it only makes sense I get the result I was aiming for, but nonetheless, seeing those numbers in real life is pretty weird. It's almost as though school wasn't entirely pointless after all. So with the heater serpentine labeled as a success, the next step is to remove any residual glue from the glass, which in the case of my rubbery contact adhesive is easiest done by rubbing it off with bare fingers. Crude, but very effective. Of course, you need to be very careful so as not to damage the heating element in the process. Then I remove any oils my fingers left behind with more isopropyl alcohol. In this step, you really need to avoid soaking the entire plate in IPA, lest it might also dissolve the spray adhesive currently holding down your aluminum and you'll have a very bad day. So a damp rag, but nothing more. Finally, to protect the fragile heating element and to permanently attach the aluminum to the glass even when the spray adhesive gets destroyed by the heat, we cover the entire surface in a layer of kapton tape. The only spot you'll want to leave out is obviously the connection pads for the power leads. Tell you what, this turned out awesome! I love the color of the kapton on the aluminum. Now, I kind of suspect those steel washers to be at fault for adding those excess 0.2 ohms, not the aluminum oxide, because if I try to measure these directly, it's really hard to get a good connection, as you can see here, and they do sometimes show up as roughly 0.1 ohm on the multimeter. So to get to the bottom of it, I made 2 aluminum washers, and sure enough, they don't show up at all. So it really must have been the washers. Let's install these and see what we get then. Well, there we have it, 3.18 ohms. Off by 100th of an ohm, and that's likely still due to bad connections. The cable itself will have more than that. Total success, I'd say. Only thing left to do now is to fire it up and see how hot it gets. Everything is ready to go. The glass is the right side up, aka the way it's going to be on the printer with the heating element underneath. I have a thermometer, I have tape to measure the real life surface temperature, like this. Multimeter to measure current, power supply is up and running, I just need to plug it in. Temperature is currently at 21 degrees Celsius. Here goes nothing. 3, 2, 1, go. Okay, 5.6 amps flowing. It's worth noting this number is slightly skewed by the multimeter. And it is getting slightly warm already. 25, 26, 27. Yeah, this is working. Current is dropping due to the aluminum heating up. 40, 64 degrees Celsius, already past PLA temperature. The aluminum is getting slightly wrinkled now due to thermal expansion, which is totally to be expected. But other than that, everything seems to be holding up just fine. It's now getting hot enough that I can burn my hand on it, which is great news. The amperage has dropped to 5 amps. Temperature coefficient of the aluminum is starting to take effect. 77 degrees. Everything still looks fine, although a little bit wrinkly. Well, if that's not a success, I don't know what is. Now I just need to wait for the temperature to stabilize, and then we'll see what the maximum temperature this thing gets to is.
20 minutes later.
It leveled out at just over 90 degrees Celsius, which is unfortunately quite a bit less than the 120 C I was aiming for, but shouldn't come as a surprise seeing as the power draw dipped under 100 watts due to the temperature coefficient of the aluminum driving up resistance. It's a little bit disappointing, but given how smooth sailing everything was after those initial difficulties getting the machine to work, I am more than happy to take it. I don't even know what filaments would require a heated bed at over 75 C anyway. Plus, this clearly isn't the most advanced 3D printer out there, so I probably won't really be printing finicky stuff like ABS on it. But now I wonder, 94 degrees, that would be more than enough to fry an egg, right?
One eternity later.
Well, I think it's safe to say I'm not going to be eating this egg. It's been running for well over an hour at this point, and all it did was dry out the egg white. I should have known. The glass doesn't have the thermal mass required to heat up an entire egg to the 70 degrees it needs to coagulate, and the heating element never had the oomph to do it either, but whatever, we had fun. Anyway, stupid experiments aside, we did succeed in developing a simple heated bed that is DIYable for well under $10. I mean, almost everyone has tinfoil in their kitchen, and even if you have to buy a roll of Kapton tape, you only need very little of it. Granted, I didn't reach the 120 degrees I was going for, but for most normal PLA and PETG printing, it should still easily be sufficient. And let's be honest, if you want to be printing fancy stuff like nylon, you probably won't be hacking together a 3D printer out of crap for the price of 2 filament spools. That said, I'm still struggling with an incredibly undersized power supply. If you can find 2 of these laptop power bricks with identical output current, just put them in series. It'll double the power along with the voltage. I may at some point do a revised version using precisely that approach. I hope you enjoyed. Huge thanks to my patrons and welcome to yet another one. It's really good to have some peace of mind in times when I'm not doing sponsorships because it allows me to be more picky with the ones I do take on. Like, I didn't realize until now, after talking to a few other companies about potential partnerships, how lucky I was to get PCBWay as my first brand deal. Big corporations and 3D printer companies in particular are pretty pushy about product reviews, so I'm quite glad I was able to get some experience in this area before being dunked into it head first. Anyway, next video we're gonna do the electronics, and that may include printing the first Benchy. See ya then, bye bye!